I want to start by telling you what I didn't know, because I think it's more honest than pretending my own work settled a question that, even now, decades after my death, remains one of the most genuinely unresolved problems in theoretical physics. When Hartland Snyder and I worked through the mathematics of a collapsing star in 1939, we could describe with real confidence the outside of a black hole, the event horizon, the point past which light itself can't escape, the gravitational effects an outside observer would measure. What we could not describe with anything like the same confidence was what happens to the matter itself once it passes that boundary and continues collapsing inward. Our own equations told us something that troubled me deeply at the time, and that has troubled essentially every physicist who has worked on this problem since. The mathematics predicted a singularity, a point at the very center of the collapsed star where density becomes infinite, where the curvature of space-time itself becomes infinite, and where the equations of general relativity simply stop producing meaningful answers. I want to be precise about what that means because I think it gets misunderstood. It's not that the physics becomes complicated at that point. It's that the theory itself breaks down entirely. General relativity, extraordinarily successful everywhere else we've tested it, essentially throws up its hands at the center of a black hole and tells you it has nothing more to say. I never resolved that problem in my own lifetime, and I want to be honest that I didn't expect it to be resolved quickly by anyone else either. A genuine singularity, an actual point of infinite density, isn't the kind of thing physics usually tolerates for long as a final answer. Historically, whenever a theory predicts an infinity like this, it's usually a signal that the theory is incomplete, that it's being pushed into a regime where some other physics not yet accounted for needs to take over before the mathematics actually breaks. I suspected, even in 1939, that general relativity alone probably wasn't the final word on what happens at the center of a collapsed star. I just didn't have the tools or the theoretical framework to say what the missing piece might be. The missing piece, as physicists came to understand more clearly in the decades after my death, is almost certainly quantum mechanics. This is where the real difficulty of this problem lives, and I think it's worth explaining clearly, because it's not simply a matter of two theories disagreeing at the edges. It's that we have two of the most successful theories in the history of physics: general relativity, which describes gravity and the large-scale structure of space-time with extraordinary precision, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales with equally extraordinary precision. And at the center of a black hole, both theories are trying to describe the same physical situation simultaneously, and nobody has ever managed to make them agree with each other in that specific regime. Quantum mechanics tells you that matter, at sufficiently small scales, doesn't behave the way general relativity's smooth, continuous picture of space-time assumes it does. Quantum theory is full of uncertainty, of particles that don't have precisely defined positions, of a kind of irreducible fuzziness built into the fabric of reality at small enough scales. General relativity, by contrast, treats space-time as a smooth, continuous fabric that curves and bends in response to mass and energy with no such fuzziness built in anywhere. At the center of a black hole, where matter is compressed to a scale small enough that quantum effects should in principle become important, you need a theory that correctly combines both pictures. A theory of quantum gravity, and despite nearly a century of extraordinarily talented physicists working on exactly this problem, we still do not have a complete experimentally verified theory of quantum gravity. This remains, I think, the single largest unresolved problem in all of theoretical physics. So when I hear that scientists have finally figured out what happens inside black holes, I want to walk you through what's actually true in that claim, because there has been real, substantial progress, genuinely important progress, the kind that would have surprised and excited me tremendously had I lived to see it. But it's progress on a related question, not a complete answer to the original one Snyder, and I left unresolved. The progress that I think deserves the most attention concerns something called the black hole information paradox, a problem that didn't even fully exist as a clearly articulated puzzle during my own lifetime. Because it required Stephen Hawking's later work on black hole thermodynamics to bring it into focus, Hawking showed in the 1970s something that surprised nearly everyone in the field, myself included, had I lived to see it, because it seemed to contradict the very definition of a black hole that Snyder and I had worked with. Black holes, Hawking demonstrated, are not perfectly eternally black. Through a subtle quantum effect operating right at the event horizon, black holes very slowly emit radiation, now called Hawking radiation, and in doing so, they very gradually lose mass and shrink over timescales so long for a stellar mass black hole that they dwarf the current age of the universe many times over, but finite nonetheless. Here is where the real difficulty emerges, and it's a difficulty that connects directly back to quantum mechanics in a way that troubled physicists for decades. Quantum mechanics has a principle at its core, one of the most fundamental and well-tested principles in all of physics, called unitarity, which essentially guarantees that information is never truly destroyed. If you know the complete quantum state of a system at one moment, the laws of quantum mechanics guarantee you can, in principle, always trace that state backward or forward in time without any information simply vanishing from the universe. But if a black hole slowly evaporates away entirely through Hawking radiation, and that radiation appears from every calculation Hawking originally performed to be essentially random and thermal, carrying no detailed information about what fell into the black hole in the first place, whether it was a star, a spaceship, or a stack of books, then it seems as though all the information about whatever fell in has simply been destroyed once the black hole finishes evaporating. And that outcome directly violates one of quantum mechanics' most sacred principles. This became known as the black hole information paradox, and for decades it stood as one of the deepest, most stubborn contradictions between our two best theories of physics. Either general relativity's picture of black holes was somehow wrong, or Hawking's calculation of the radiation was missing something, or quantum mechanics' guarantee that information can never be destroyed needed to be abandoned entirely. And none of these options sat comfortably with physicists working on the problem, because all three of the underlying theories had, in their own domains, been tested and confirmed to extraordinary precision. What has actually changed in the years since, and what I think honestly deserves the description "scientists finally making real progress," is a body of work developed largely in the 2010s and into the 2020s using mathematical tools that didn't exist in any usable form during my own working life. The most significant of these tools goes by the name of the holographic principle, an idea rooted in what's called the AD-SCFT correspondence, first proposed by the physicist Juan Maldacena in 1997. I want to try to convey the strangeness of this idea plainly, because I think it's genuinely one of the more remarkable developments in theoretical physics since my own death. The holographic principle proposes that a theory of gravity operating in some region of space can be mathematically equivalent, not just similar, but exactly, precisely equivalent, to a completely different theory, one without gravity at all, operating on the boundary of that region, one dimension lower. It's called holographic because of the analogy to an ordinary hologram, where a full three-dimensional image can be encoded entirely on a flat two-dimensional surface. Applied to black holes, this principle suggests that everything happening inside a black hole, including whatever is happening at that troubling central singularity, might be completely and exactly describable using a quantum theory living on the black hole's boundary, its event horizon, a theory that crucially doesn't include gravity, and therefore doesn't run into the same singularities and infinities that plagued our original general relativistic description. If this correspondence is correct, and a great deal of theoretical work over the past 2 decades has tested and supported it in various mathematical contexts, it suggests something genuinely important about the information paradox. Because the boundary theory is an ordinary quantum theory, information falling into the black hole isn't actually destroyed at all, even though it certainly looks that way if you only track things using the original gravitational description. The information isn't lost. It's encoded in some extraordinarily scrambled and difficult to decode form in the correlations of the radiation the black hole eventually emits. The most direct evidence supporting this picture came from a set of calculations developed around 2019 and refined over the following several years, involving mathematical structures called replica wormholes, developed by several groups of physicists working somewhat independently, including work by Ahmed Almheri, Netta Engelhardt, Donald Maroff, Henry Maxfield, and others building on ideas from a broader collaboration in the field without walking through the full technical mathematics, which is considerably beyond what I could do justice to here. The essential result was this. When these researchers recalculated how much information should be encoded in Hawking radiation using more sophisticated mathematical tools than were available to Hawking in the 1970s, they found that the radiation does, in fact, carry out the full information content of whatever fell into the black hole, consistent with unitarity in a way Hawking's original calculation had missed. Crucially, this calculation suggested that the information doesn't leak out gradually and smoothly throughout the black hole's evaporation. It stays hidden for a very long time, and then begins escaping much more rapidly partway through the evaporation process, at a point now referred to as the Page curve turning over, named for physicist Don Page, who had actually predicted this specific pattern back in 1993, long before the mathematical tools existed to actually demonstrate it directly. I find this development remarkable for a reason that goes beyond the specific physics involved, though the physics itself is remarkable enough. What these calculations represent is genuine mathematical progress on reconciling gravity and quantum mechanics in a specific, well-defined context, using tools that simply didn't exist for most of the 20th century. It doesn't yet constitute a complete theory of quantum gravity. The holographic techniques that produce these results work most cleanly in a mathematically idealized version of space-time called anti-de Sitter space, which has different and, in some ways, more convenient geometric properties than the actual universe we live in. Extending these results rigorously to our own universe's geometry remains an active and genuinely unresolved area of research. But the fact that physicists can now show in a controlled mathematical setting precisely how information can be preserved, even as a black hole evaporates, represents the first time anyone has demonstrated a fully consistent resolution to a paradox that had for decades seemed to force a genuine contradiction between our two best theories of physics. I want to be honest with you about what this progress does not yet tell us, because I think overstating it would do a disservice to how careful this entire field has had to be. These calculations tell us something important about how information behaves in the radiation a black hole emits, and they tell us that information is very likely preserved rather than destroyed, resolving the paradox in the sense that mattered most for quantum mechanics core principles. But they do not, even now, give us a complete, verified description of what physically happens at the singularity itself. The very question Snyder and I left open in 1939. The holographic techniques largely sidestepped the singularity by working with a boundary description rather than directly modeling the interior geometry all the way down to the center. Some more recent theoretical work has begun probing what these holographic methods might imply about the interior geometry more directly, including intriguing suggestions that what looks like a singularity in the classical general relativistic picture might correspond in the full quantum description to something quite different. Not an infinitely dense point, but perhaps a highly quantum, strongly interacting region where the classical notion of smooth space-time simply stops applying, replaced by something we don't yet have a fully developed physical picture for. This remains an active frontier, not a settled conclusion. I think what I find most satisfying about this entire body of work, looking at it as someone who spent real time wrestling with the original singularity problem and never came close to resolving it myself, is how directly it validates a suspicion I held but couldn't substantiate back in 1939. I believed, even then, that a genuine, infinite density singularity probably wasn't physics's final word on the matter, that some deeper theory incorporating quantum effects we didn't yet have the tools to properly combine with gravity would eventually need to take over and give a more complete answer. I had no way in 1939 to say what that deeper theory would look like or how it might resolve the problem. The holographic principle, replica wormholes, the resolution of the information paradox, none of this was available to me, even as speculation, because the entire mathematical framework these ideas depend on wouldn't be developed for decades after my death. What strikes me most, considering all of this from wherever this reflection is coming from, is how the field has actually progressed, not through a single breakthrough that suddenly explained everything, the way popular retellings of scientific discovery sometimes suggest, but through decades of incremental work, false starts, competing proposals, and mathematical tools developed initially for entirely different purposes that turned out unexpectedly to be exactly what this problem needed. Maldacena's original holographic correspondence wasn't developed specifically to solve the black hole information paradox. It emerged from string theory research, pursuing different questions entirely, and its application to black hole physics came only later, once physicists recognized what tools it might offer for a problem that had sat unresolved since Hawking's original work in the 1970s, which itself built on a foundation Snyder and I had laid unknowingly decades before that. So when someone tells you that scientists have finally figured out what happens inside black holes, I think the honest answer is more interesting and more true to how physics actually works than a simple yes or no. We understand now with real mathematical rigor in specific theoretical contexts that information falling into a black hole is very likely preserved rather than destroyed, resolving one of the deepest paradoxes in 20th and 21st century physics. We do not yet have a complete, verified picture of the singularity itself, of what physically happens at the exact center where my own 1939 equations simply stop making sense. What we have is genuine, substantial progress, the kind that would have meant a great deal to me had I lived to see it. And one of the hardest problems my own early work in gravitational collapse ever opened up, with the hardest part, the true unification of gravity and quantum mechanics at the deepest level, still very much an open question for whoever takes up this work next.